I'd like to start by asking you what you associate with the term civilization. Probably most of us here in Zurich think we're pretty civilized. Certainly most of us here at WORLD.MINDS. But we read literature, we work in fine buildings, some of us think grand scientific thoughts occasionally, maybe we go to the opera. But I would like to argue that civilization is rather just a measure of the state of progress in material science. Because from the Stone Age to the Bronze Age to the Iron Age, every major advance in human civilization was driven by a development in materials. So much so that we label our historical eras after the materials that dominated their times. Today, we often say that we're living in the Silicon Age because silicon forms the core of the microelectronics that enable much of our modern way of life. Not just our computers and mobile phones, but communication, transportation, the list is endless. And over the last decades, we've made tremendous progress in the properties of silicon devices, enabling, for example, the transition from clunky old desktop computers to sleek smartphones, all with the same material, silicon, at their core. But this silicon revolution will soon be forced to come to an end as we start to run into fundamental physical limitations that are set by the size of the individual atoms that make up the silicon material. And so this steady march towards faster, lighter, cheaper products with more and more capability can't continue, at least not within our existing framework. Well, you might think that's fine. The controls on my iPhone are certainly smaller already than I can see without my reading glasses. But in fact, it poses a profound problem for society. Worldwide use of microelectronics is increasing so rapidly that by most estimates, half of global energy consumption will be used by information technologies within a couple of decades. And this is clearly not sustainable. So we need to take the step beyond the Silicon Age. And to do that, we need a new material. And as a material scientist, I get paid every day to go to work to develop that new material. 20 years ago, I was a young, very young, in fact, postdoctoral researcher working on ferro-magnetic materials. These are materials with aligned magnetic dipoles consisting of north and south magnetic poles. And I was working in a laboratory that specialized in ferroelectric materials, which are materials containing aligned electric dipoles made up of positive and negative charges. And my plan had been to take the tools and the techniques that my host group had developed for ferroelectric materials and apply them to the study of ferromagnets. The ferro, in both terms, reflects underlying physics between the two materials classes. But I noticed that the kinds of materials that I was working on were very different from those of my colleagues. A typical ferromagnetic material, for example, is a black metal like iron, whereas a typical ferroelectric material is a transparent ceramic. Barium titanate would be a prototypical example. And I could find no materials that belonged into both classes. And this really bothered me, finding the answer to the question of why are there so few magnetic ferroelectrics became, I'd say, something of an obsession for me. And what I discovered was really very simple, that the kinds of atoms that are good at making magnetic dipoles in a material have different chemistries from the atoms that are good at making electric dipoles in a material. They just sit in different places in the periodic table. But I was able to show that there's no fundamental physical reason why ferromagnetism and ferroelectricity should not coexist. There's no law of physics preventing them. And so, armed with this knowledge that magnetic ferroelectrics are at least in principle possible, my collaborators and I were able to develop an entirely new class of materials, we call them multiferroics, that indeed are simultaneously ferromagnetic and ferroelectric. We did this in two ways. First, by designing new materials that incorporate both types of atoms, the atoms that are good at magnetic dipoles together with the atoms that are good at electric dipoles, like the bismuth iron oxide shown on the left here. And second, by engineering new crystal structures that trick magnetic atoms into forming also electric dipoles, like the yttrium manganese oxide on the right. So why are multiferroics important? Well, magnetic materials are complementary to silicon in contemporary technologies. Where silicon processes the information, magnetic materials are used for storing it. And magnetic materials are very good at this because these magnetic data bits, which represent the ones and zeros of digital electronics formed from the opposite orientations of the magnetic dipoles, are very stable. They can be rather small, and they can be accessed readily. But magnetic materials come with a cost. Generating the magnetic fields that are needed to control the magnetism requires bulky, heavy components that use a lot of energy. Maybe you once injured your knee and went to the hospital for an MRI, and you remember this enormous machine that was needed to generate the magnetic field. But now imagine the possibilities posed by a material that's both magnetic and ferroelectric. So in our multiferroic materials, we've been able to control the magnetism using an electric field. And compared with a magnetic field, an electric field is made from components that are tiny, very light, and use vanishingly small amounts of energy. So through their electric field control of magnetism, our new multiferroics are poised to enable entirely new device technologies, entirely new ways of designing information technology. Maybe we're about to enter the new multiferroics age. Now, of course, there's many factors which decide whether a material makes it into a technology. So just in case multiferroics don't define the course of human civilization, I'll end with an example of multiferroics research that has no obvious application, but I hope you'll agree still has value. And I do this in part to make a slightly political point. First, that fundamental research in materials science is important even if it doesn't lead to anything useful. Uncovering the romance of electrons and atoms interacting in a solid is comparable to discovering a new elementary particle at CERN or listening to the Tonhalle play a Brahms symphony. They're all activities that as society we consider valuable to invest in. And with materials research, there's also a second aspect, which is if we work only on materials for which we already have an application in mind, then by definition, we're limited by what we've already been able to imagine. And with such a kind of restricted mindset, we'll never develop anything entirely new. We'll never open new directions. So when we started working on multiferroics, there were certainly no device physicists waiting eagerly on materials because the materials didn't exist. The ideas had not been developed. And it takes, I think, such undirected, unrestricted fundamental research, not just in materials, but in any field, to open up really new paradigms. This is an image of the surface of yttrium manganese oxide taken by my colleague Manfred Fiebig at the ETH, with the black and white regions representing opposite orientations of the electric dipole moments. When I first saw this image, it just shocked me. I think in the same way as when I heard my first late Beethoven string quartet. It's not only is it achingly beautiful, but there was also nothing in my experience of how such patterns of electric dipoles looked in conventional ferroelectrics to lead me to expect such a picture. It came completely out of nowhere. And in the process of our understanding why a multiferroic has such a pattern of electric dipole moments, what we discovered was that the intersection points between the dipoles that we see on the surface in 3 dimensions actually form strings. They form one-dimensional lines that are shown here in red. On the right, I'm showing for comparison a simulation of the formation of cosmic strings by Martin Kunz from the University of Geneva. These are textures that are proposed by leading cosmology theories to have formed in the early vacuum immediately after, in the early universe from the primordial vacuum immediately after the Big Bang. And of course, it's tough on cosmologists. It's very difficult to study cosmic string formation directly because one can't go and replay the Big Bang in the laboratory. But we've been able to show that the formation of the electric dipoles in our ferroelectric material is formally mathematically identical to the proposed formation of cosmic strings in the early universe. So now in our laboratory, we can measure, using our multiferroic material, the properties that cosmologists would like to know about cosmic strings. Do they exist? How do they form? What are their properties? How do they evolve? Now, our tabletop cosmology experiments are unlikely to lead to an improved iPhone, and certainly not likely to accelerate the dawn of the multiferroics age. But they captured the public imagination to an extent I had certainly not anticipated, and led, for example, to this article in National Geographic saying that the universe's existence may be explained by our new multiferroic material. Now, I show you this, of course, a little bit in jest, but not entirely, because after all, explaining the universe, or at least some small corner of it, is what defines me as a scientist. I hope I've conveyed to you my passion for developing, exploring, designing the new multiferroic materials that form my little corner of the universe, and in turn my optimism for the future of human civilization. Thank you for listening.